All right, let me stop sharing so you can...
Okay. Let me start. Okay, so thank you very much for inviting me. You know, let me echo my sentiment that I hope this will be more of a conversation. So please do feel free to jump in anytime with questions. So today I'll be presenting C cubed, which is our advanced concept for an E plus E minus linear collider. And, you know, special thanks goes to Katerina. She's been helping me in particular over the past couple of months in putting these slides together and exploring the scenarios that we'll discuss today. But of course, many people have contributed directly and through discussions. So a more accurate list of contributors to this presentation is really from our SNOMAS LOI and plus some recent experimental activities from collaborators at SLAC shown over on the right here. So I want to begin today with a little bit of the view of the, let's say, the accelerator physicist in this scenario. And what I think I have to highlight is that there really has been a breakthrough in the performance of RF accelerators over the last few years. And it comes down to two distinct topics. The first one is actually in the design of the accelerators themselves. So we've been putting forward a great deal of effort in exploring how we can optimize the performance of the accelerator from the RF perspective by maximizing each cavity's design. And when you do that, you come up with these cell geometries, which are reentrant and highly optimized. They minimize both the surface electric and magnetic field, but you run into a problem with how you can couple power into these structures. And Sami Tantawi a few years ago, along with some collaborators, proposed that this could be done with a manifold which runs down the side of the structure. And that allows you to couple into each cell individually. And if you can do that, then you can preserve the optimized structure of the cavity, but also make a very, very efficient structure. So it has a very high shunt impedance. And that's just a measure of how much power you need to establish the gradient for accelerating the particle beam. And that's independent of the beam power that you're going to put through here. So this is something that's very critical, and it's something that we're always fighting against. The other key innovation that is very important for C cubed was realized during the study for high gradient operation. There was a collaboration between SLAC, CERN, KK, and many other institutions that participated. They were exploring the physics of breakdown at high gradient and normal conducting structures. And one of the key discoveries there was the role that the material strength plays in determining the breakdown rate. So breakdown is the result of strong electric and magnetic fields in the material. They create these very small surface protrusions that end up emitting electrons that forms a plasma, and then you get an arc in your cavity. And this, of course, is bad if you're operating an accelerator that's many kilometers long. And what you see here in this plot is that as the material strength goes from soft copper to these hard copper silver alloys, the performance of the structure improves in terms of breakdown rate versus the achievable gradient. But it's not only from the material properties itself, but it's also from the temperature of operation that you can make a significant difference here. And what you're seeing here in this cluster of data is a structure that was operated at 45 degrees Kelvin, and it performed significantly better in terms of the achievable gradient. Now, operating at cryogenic temperatures has an additional benefit besides getting to higher gradient. It also reduces the amount of RF power that's required to achieve the same gradient in the structure. And this is very important in the case of linear colliders because the RF sources themselves that power the main linac are really the key cost driver if you use a traditional structure. So reducing the amount of power that you need in order to establish that gradient is a big improvement. Now, we are not proposing to operate these accelerators at 45 degrees Kelvin. We're actually planning to work closer to 77 degrees Kelvin with structures that are immersed in liquid nitrogen, as is shown here in this little lab setup. You can see the copper structure immersed in LN here. And the reason for that is several-fold. First off, there's large-scale production of liquid nitrogen. It has a great heat capacity, so it's good for cooling the structures when there's high-power RF going into them. And overall, it actually has a relatively small impact on the electrical efficiency. So it's not as efficient to operate low in temperature, although it saves a significant amount of RF power. And the reason for that is you do have to cool the energy that's deposited into the structure at the cryogenic temperature. And so what you have is the structure is basically 2.5 times more efficient in terms of the RF power that it needs. This is further enhanced by the efficiency of the klystron, which is producing the RF power. So you save an additional factor of 1/2 in terms of the overall efficiency of the system. But then because of course, the laws of thermodynamics, your cooling efficiency, low in temperature is quite low, only about 15% in a practical system. So overall, your efficiency compared to room temperature operation is reduced, but not by a terrible margin. So something that we can live with. So it was really this combination of an improved accelerating structure design as well as operation at cryogenic temperatures that motivated us to pursue a new concept for a linear collider, which we've termed C-cubed, the cool copper collider. So it's based off of technology that's been developed at SLAC, and that of course we're very passionate advocates for. One of the key goals for us was to achieve a high real estate gradient. So what we mean by this is that the actual footprint of the machine will have a gradient eventually on the order of 110 megavolts per meter. In addition, there's some other possible advantages with this technology. Through a collaboration with UCLA, we're pursuing the possibility of developing a high brightness polarized gun, which could eliminate one of the damping rings. And finally, this really needs to be a scalable technology that's optimized for reaching multi-TV of operation. So the majority of my talk today is going to be centered on getting to 250 GeV center of mass, but we really think this is an approach that can let you push out to multi-TV. So if you, I'll share these slides after the meeting, but there's a couple links for here. This is for our study at 2 TV center of mass, the C-cubed LOI for SNOMAS link, and then a previous colloquium in case you're interested. In the very near scale, a near-term timeline, what we're looking to do in the next couple of years is perfect the meter-long accelerating structure. There's a prototype here shown on the top right. Incorporate Wakefield damping and develop a structure that's compatible with cryogenic operation. And then roughly 4 years after that, we're hoping to be testing some modular GeV cryo modules, and then we'll talk about that a little bit in more detail. And eventually to operate in parallel with High-Lumi LHC, or towards the end of the High-Lumi LHC run, with 250 GeV center of mass. The other figure that you're seeing over here actually was an earlier test that we did with an X-band prototype. So this is a slightly different operating frequency, higher by a factor of 2 than what we've settled on for this study with C-cubed. But it did achieve 150 megavolts per meter while operating at cryogenic temperatures. So we really think this is a practical near-term technology for linear colliders. So let's take a look at what's going on internationally. So here's a rough timeline that shows the LHC operation and the High-Lumi LHC upgrade. And of course, the study of the Higgs, there's really a complementarity between hadronic and leptonic machines, whether it's in the pursuit of higher energy for looking for exotic particles, or if we're focusing more on precision measurements. But I think everyone in this audience knows this better than I do. But what's the goal in terms of beyond High-Lumi LHC? Well, there's a couple of key things that the community is very interested in. The first being the establishing of Yukawa couplings with greater precision, And secondly, establishing the self-coupling. So being able to reach higher in energy with E plus and E minus. So looking at this specifically in a scenario where, for example, high Lumi LHC would be followed by FCCEE, we would first be looking at Higgs couplings to a few percent, and then getting down to the percent level with FCCEE, and only moving on to fraction of a percent or self-coupling later in time. And before I jump ahead, what we're interested in is understanding, could we be competitive with this timeline, and could we possibly produce physics for the Higgs on an earlier timescale that's better aligned with high Lumi LHC. So what I'm showing here is what we think is really the best timeline for the physics that C³ can enable. It starts in 2023, sort of at the outset of the SNOMAS and P5 process, where we would be putting together a proposal for a demonstration facility that would demonstrate the fundamental sort of 1 GeV cryomodule that would be needed for the C³ LINAC. That demonstration facility would run roughly for a timescale of 5 years. And after that, we would really have finalized the technical demonstrations that were needed to realize the machine. Of course, in parallel to this, we'd be working on a proposal for the full C³ accelerator that could reach 250 GeV center of mass, with an option for upgrading to 550 GeV center of mass. The proposal from that would then lead into the construction and commissioning phase for the 250 GeV center of mass facility. And we think that that timeline would take roughly 10 years for it to build. And I'll go through some of the reasons why here closer towards the end of the talk. One of the most interesting things that we want to highlight and get feedback from you actually on would be the possibility of turning on earlier during this construction and commissioning phase, and actually operating the main LINAC at 91 GeV center of mass to look at the Z boson. And the real goal here is to commission the accelerator complex, commission the main LINAC, get the detector working, and start to produce some physics as early as possible. I want to be clear, though, that the number one goal here is to produce the Higgs as soon as possible. So we really only want to support this if it could be done in a way that speed things up. So the reason that this is possible is because you would build out the main LINAC, moving back from the final focus towards or further away from the interaction point. And so the main LINAC that could produce 250 GeV center of mass would only be ready towards the end of this 10-year time period, and we'd reserve a year at the end for commissioning that 250 GeV center of mass. So right before 2040, we would be turning on at 250 GeV center of mass, and we would plan to operate there for a decade. Now, one of the interesting things that we'll talk about today is that we would construct the main LINAC in a way that it would be operating at a lower gradient, and you could be upgrading the RF power that was available in parallel. So while the LINAC is producing the Higgs for study at 250 GeV center of mass, and by the time you finished this 10-year program, you would immediately be prepared to commission the machine at a higher energy. So somewhere in the range of 500 to 600 GeV, and that sort of depends on the details of exactly what gradient you'd want to operate at and what the length of the main LINAC would be. Then, of course, you would be operating at this point for another significant period of time, and you could explore the possibility of, for example, increasing the length of the main LINAC further. So I want to pause here and see if anyone has any questions with the timeline on this slide.
So I'm wondering if you could just say a couple words. I mean, it's very interesting about what sort of sets the timescale for, let's say the 250 GeV operation being 20 years from now, approximately. can you give me an idea of like what sort of R&D has to be done in order to make it on that time scale?
Great question. So let's say it's my opinion, but so it's my opinion that because of the great work that has been done by the CLIC community and the ILC community, really all of the components of the accelerator complex have been proven to a high level of technical readiness. And the only significant technological demonstration that's needed is the operation of the cryomodule, which would form the main LINAC. And that's specifically what we would be focused on during the operation of this demo test. And realistically, it seems like that would take on the order of 5 years because some construction would be involved, some significant amount of procurement. And plus, in parallel with that, you'd be putting together the full proposal for the 250 GeV center of mass accelerator complex. So there's roughly that 5-year chunk of time, which is one of the fixed variables. And then the second one is actually how long it would take to construct the full accelerator complex. And it'll be more apparent later on in the talk, but one of the very nice things about doing it over the decade timescale is that you really match up well with what could be produced by industrial partners in terms of the components that are needed for the main LINAC. And it would be in a way that you would transition smoothly into the RF upgrade. So basically, the production of RF sources would remain constant over this 2-decade period. And that would let you do it in a way that really, you'd have long-term partners in industry. They would really be focused on bringing the cost down. And I think makes it a very practical and realizable machine.
Okay, thank you.
Sorry, can I ask a question here as well?
Yeah, please.
Yeah, so this timeline, I mean, I think takes into account that, or it assumes that there is no discovery of a new particle, at least at the mass greater than 300 GeV. So what if for instance, in the high Lumiere phase of the LHC, a new particle is discovered? How this program can be adjusted accordingly?
That's a great question. So what you could certainly adjust immediately would be getting up to an energy between 500 and 600 GeV. Like there's nothing, the main LINAC that you're constructing is capable of this energy here. The question is just how much RF power do you install during the initial construction phase? And that, at the end of the day, that comes down to this question of money and how big of an investment you'd make in the industrial facilities that were needed for it. If you needed to go beyond the range of 500 to 600 GeV, you would need to increase the main LINAC length. So you'd have to add additional tunnel.
Okay, so with the same technology, you can go to the higher energy by just extending the length of the accelerator.
That's right. So the original starting point for our study was actually a 2 TeV center of mass. And our design is actually optimized for 2 TeV center of mass for the main LINAC. And what we've been working on over the last, roughly 6 months to a year is understanding how we could start to realize this and what the plan would be in the near term or the relative near term for 250 GeV center of mass.
Okay, thank you very much.
Emilio?
Yeah.
If I may, I have a couple of questions. One is this demo test,
Yes.
which presumably can be done sort of essentially now, right? So basically,
Yes.
we can start thinking about it now. Can extension of original LCLS, which is warm LINAC, right? So single pulse, single bunch, right? So can it be kind of augmented with this demonstration facility or C-cube facility to push the energy further up by substantial factor? So is it a fiction or feasible?
You will see the last presentation of, or I'm sorry, the last slide of this presentation will show a couple of C-cubed LINACs boosting the energy of LCLS. so it's absolutely appropriate. The structure itself operates at twice the frequency of the main LINAC for LCLS, so it's fully compatible, and it could either add on a little bit of length, or for example, it could replace a section of the LINAC and operate at roughly, if it was at its full gradient, it would be 5 times the gradient of LCLS.
5 times the gradient, so basically, okay.
Yeah. So this is actually something we're talking about, and then the question would come down to sort of timeline and funding and all of these things. But certainly the technology that you developed as part of this could be installed and implemented at LCLS.
Right, so within small footprint, you can say potentially double the energy of LCLS1, right?
Yeah, yes, you could. Yeah, that's right.
Okay.
And in a way that would, utilize all of the existing undulators and the gun. Another interesting thing we've talked about is possibly replacing the injector for LCLS with a cryogenic C-band gun with higher brightness, which would of course be of a very great benefit to the FEL program. So that might be another great place to demo one of the aspects of this technology. That's not required, but that would be very beneficial to the program.
Okay, and my other question was, CLIC is fighting for support, and I believe any help from any direction could be well appreciated. So given many kind of inventions and breakthroughs you guys kind of consider feasible for this C-cube concept, can any of your approaches be used in CLIC in order to make it more, I would say, feasible or more acceptable? So do you think of they can borrow, or they should borrow anything you guys kind of are talking about?
So we're actually stealing from them in many ways, as I'll show also here in a little bit.
But high Shannon structures, copper.
Yeah.
Even if not super cold, basically not at the cryogenic temperature. So could they be of use for CLIC? No.
There's a challenge with implementing our approach with CLIC that has to do with like let's say so it depends if you're saying like CLIC in the 2-beam case, which is I think what you mean, and not CLIC K. But CLIC in the 2-beam case is producing pulses that are very short, and basically the shunt impedance comes from the fact in part that the quality factor is so high for these cavities, and so they have a relatively long fill time. So it's not a great fit with the very short RF pulses that are being produced in that scenario. We are actually actively talking with the CLIC team, not only because we want more of their sort of intellectual input into this, but also because we are exploring testing one of their structures at cryogenic temperature, just to see how it does in terms of high gradient. And then if that did well, we could conceivably look at redesigning it. But at first pass, I do think it's a tough challenge. There would be some benefit, but not as large as what we see here.
Okay, thank you.
Another quick question here.
Yeah.
Yeah, I mean, I can see that this is already an optimistic timeline, but I thought you were, on one of the earlier slides, you mentioned that the idea is to have a operation, I presume, of the 250 GeV operation in parallel with HL-LHC. Did I hear that wrong? And does this 91 GeV operation impact your construction commissioning timeline?
So I mean, personally, I'm of the opinion that it will help speed up operation at 250. The reason for that is because you would turn on the injector complex, you would be sending beam through the final focus. So you'd really be tuning up the machine under operational conditions. So I would only advocate for it if it is done in parallel and in a way that does not delay the arrival of of the Higgs. Now, yeah, as far as operation in parallel, right, it's only really the tail end of, let's say, high Lumi LHC. I don't know off the top of my head if these are the exact dates for the high Lumi LHC run. But yeah,
close enough. Yeah.
Yeah, I think in practice, I think at this time, proposing a 10-year period to build the full accelerator complex looks reasonable. And we will, as we go forward, we will try and make that as short as possible.
Okay, thanks.
Perhaps we should move on to the rest of your slides. Some of the questions are probably going to be answered later, right?
Sure, sure. No, but this was great. Thank you for all the questions. All right. So, so just a couple of comments first about sort of the comparison between linear and circular colliders. So of course, well, first, you know, E plus E minus beams, it's a relatively benign environment compared to what we would have from high Lumi LHC in the detectors. And in particular for linear colliders, they do have a lower luminosity compared to circular ones below 300 to 400 GeV. But because of the time structure, they're a pulse machine. It does make for significantly lower power consumption in the detectors. It's something that you can pulse, and you need less material because you don't need active cooling in the detectors. For circular colliders, their strength, of course, is having very high luminosity at the lower energy range, but struggling if they are E plus, E minus to get above the sort of 350 to 400 GeV because of synchrotron radiation. And then without, with the beam structure that they have, they cannot, the detectors cannot operate in a pulsed mode. So yeah, maybe this is a sort of saying things in a little bit different way, but the key statement here is really that we can get significant power savings in the detectors for linear colliders, and this shows up as a benefit in terms of how they are cooled. Of course, for the lower energy range, we are fighting against the great luminosity that's achievable with the circular machines. So now that I've sort of presented the landscape, how could we get C-cubed underway as a project with the timeline that's both compatible and competitive on the global scale? And what we are really exploring and proposing is that we would build a machine that's capable of reaching 250 GeV center of mass immediately, but provide an upgrade path. We are exploring this commissioning run when the main LINAC is roughly 1/2 complete. This would be to commission the injector complex and the beam delivery system. We'd run at the Z mass in order to commission the detector. It could also possibly be used as a technology demo for things like a gamma-gamma collider. You may have heard of the XCC concept, which some of us are also involved with the real goal of delivering physics early and often from accelerators, particle physics, FELs, but of course, understanding that the #1 goal is to study the Higgs. We want a machine that builds a foundation for upgrades. So the main LINAC, at least for the first upgrade, would be fixed in length, and we would upgrade the gradient that the LINAC is operating at a later date. Ultimately, that gradient would be 120 megavolts per meter in the structure itself. So we're starting somewhere in the range of 70 to 85 megavolts per meter. So why is this a benefit for getting started? Well, the biggest benefit is it ends up making the machine cheaper for the first stage. So there's reduced peak power, which means less money. It's also lower risk in terms of many of the technical aspects. So you get a lot of power margin for the structure. You get a lot of gradient margin in terms of the breakdown rate. And then finally, I think this one's also very important. You get margin in terms of the length. So if, for example, some of the cry modules, or let's say some of the RF sources are not operational, you can make up for that gradient by pushing harder on other sections of the complex. So we want to get this program off the ground very quickly. So we're exploring commercial options. We're in discussions with vendors to deliver sources that are on the order of 65 megawatts per meter to launch the program. And our studies really work off of the CLIC case study. And if you dig through the details of that, their RF source cost is roughly $7 per peak kilowatt. So that is a key parameter in our assumptions. Oh, I'm not sure my figures are not showing. You don't see the figures, do you?
No.
Oh,
It's very strange. My apologies. One moment, please. Huh.
you can see it on.
I don't know why, but I can see them in the scroll bar on the left, but now even on the main slide, they're not showing up. Okay, I've literally never had this happen before. If you could give me just one moment, I have a PDF. I'm hoping the PDF did not have this problem. One moment, please. Phew, okay, all right.
Okay.
Very sorry, but let me switch to the PDF for a moment. Can you see this?
Yep. Looks
Yeah.
good.
Okay, so let me just keep going then. Sorry about that. Okay, so to develop our collider concept, we started a study a couple years ago. That's the archive paper that we mentioned, initially looking at 2 TV center of mass with a single beam power of around 9 megawatts. And really the only way we could do this was to lean on existing collider designs to inform our initial selection of parameters, in particular CLIC and NLC when it comes to the beam aperture that was needed, bunch charge, and how we can handle the wakes in the structure, the wake fields. And now we're moving our study back from 2 TV center of mass to see how it could be realized at 250 GeV center of mass. As far as components outside of the main LINAC, large portions of the accelerator complex are compatible between different linear collider technologies. For example, like the beam delivery and the interaction point can be identical with what was done for ILC. The damping rings have a lot in common with what has been studied for CLIC. The injectors, those do need to be adjusted a bit, but could be optimized, for example, with CLIC as a baseline, or possibly some of the R&D that we're doing could have a very significant impact. For example, with the development of a high brightness polarized electron source. So we are, very interested now at this stage in terms of growing an international collaboration. We've really started to talk more with the CLIC community, and we're planning on growing that discussion further. You can imagine a scenario where CERN and CLIC really contribute to the damping rings, alignment. Japan could be the RF systems, and of course, many other possibilities, including US partners as well. So on this slide, I'm just showing, and in the next few, I'm just going to show some of the technical details to give you a feeling for where the technology is at a moment. So this would be the RF pulse structure that we would use to power the first stage that would get us to 250 GeV center of mass. It's roughly a 1 microsecond long RF pulse that comes from a 30 megawatt per meter RF power distribution system. You see this drop here in the power in the model that I'm using. That's because I don't have an electron beam being accelerated in this model. And so this power that's missing here is the power that you'd actually be depositing into the electron beam that's being accelerated. And then here, this is shown for 250 nanoseconds in length, but you could extend it all the way out to 700, which is what we're planning for the first stage. Here you're just seeing that this 30 megawatts would give you 70 megavolts per meter in the structure. And we would have one 65 megawatt klystron every 2 meters in order to power this style of structure. And this matches exactly what the CLIC-K baseline RF module is, although it's half the frequency. So we are building prototypes of the C-cubed accelerating structure. The goal is to really understand how some of the technology that we've developed will work on the meter scale, and then to test it under the various types of operational conditions that are needed. And so we're doing this in a way that we're implementing all of these great advances that have been made in high gradient research over the last decade or so. You're seeing here, this is the actual cell geometry that we're utilizing. It has both a very low peak surface electric field as well as low peak surface magnetic field. We have those manifolds that I mentioned earlier that are distributing the RF power, powering all of the cavities. We only have one feed per meter, so keeping those part counts low. And you're seeing the actual structure as it's being fabricated here. We've now tuned our first meter long prototype. And just in the last few days, we actually tested its performance with low power while the structure was immersed in liquid nitrogen. And that's what you're seeing in this photograph here. And it did great. We also have some smaller scale structures that we're using to test at high power at the moment. Maybe I should comment that this has been tested at low power, and we have plans to test it at high power with our collaborators at Radiabeam, which is based out of Los Angeles or Santa Monica. But a smaller structure that we fabricated and are basically the equivalent cavity geometry, and that have been tested at Los Alamos National Lab for us. And over the summer, those structures were able to exceed the gradient that we need for C-cubed for over 500 nanoseconds. So this is a fantastic result for us. The C-cubed LINAC at what we envision at its maximum would operate around 120 megavolts per meter. And what you're seeing is that it does so for over 500 nanoseconds. And when we operate at this high of a gradient, we actually only plan for the pulse length to be 250 nanoseconds long. So this is, I can't stress this enough, this is a great result that they were able to produce. The big remaining technical question for us in the structure is how to damp the higher order modes. And we're pursuing an approach that utilizes a tapered parallel plate waveguide that cuts into the side of the structure. This does not really perturb the accelerating mode in any significant way, but it dramatically affects these higher order modes that are produced by the electron beam as it passes through. And in particular, we're pursuing an approach where we would coat it with nickel chrome, which has a relatively low conductivity at cryogenic temperatures. So it improves its ability to absorb RF power from these dangerous higher order modes that can destabilize the beam. So in addition to doing these small scale studies for the wake field damping, we've also launched a modeling effort to look at it in more detail. And so far that looks pretty promising in some of the first passes. I'll just highlight here that the goal is to get this kick factor below 50 volts per picocoulomb millimeter meter, which you see here, up to 15 gigahertz. And when multiplied with the quality factor for those modes, should be less than 10 to the 4. So just a couple of them are outside of this range, and so we need to do a little bit of optimizing further. And then we also need to push these simulations out to 40 gigahertz in order to prove that the damping would be good over the full needed range for the main LINAC. Sorry. So I do want to comment a little bit about the RF sources. So at least for the first stage of C-cubed, We're very interested in using commercial options because there's been a lot, of course, many decades of development, and there are production facilities that can produce these RF sources, readily today. What we mean by RF source is both the modulator for producing the high voltage pulse, as well as the klystron for amplifying the RF signal. As I mentioned before, the click K estimate, it depends on what the power of the klystron that you're utilizing, but in their study, it's around 65 megawatts per klystron. So it puts the cost here between $7 and $8 per peak kilowatt. And they are working with industry. One of their partners is CPI, which is actually located here in the Bay Area, to develop the klystron that would be optimized for their experiments related to click K. But we would be implementing basically the same technology for the first stage of C cubed. Now, long range, we do have an active RF source R&D program, which is really trying to push this cost down to $2 per peak kilowatt. And the reason for that is that's where it becomes the most advantageous to operate at this higher gradient of 120 megavolts per meter, if you consider the overall cost of the main LINAC. So as the facility is being constructed and the RF upgrade is being done, you could implement any improvements to the RF sources as you're going along and reduce the cost of the facility. So getting a little bit into the machine design itself, one of the important questions we got recently was, does this really fit into an appropriate tunnel size? And since we're using the ILC as the source of some of our costing inputs, we decided to utilize their tunnel profile in order to study how you could construct the main LINAC. Let me start with the figure over here on the left. So what you're seeing is one of these individual cryomodule units. In the initial 250 GeV center of mass, these are roughly 9 meters long, and each would produce or would accelerate the beam by an additional 630 MeV. They would be powered by 4 RF sources. What's shown here are actually modulators that are a catalog item from Scandinava, and these klystrons would be, for example, similar to what is being produced by Toshiba or Canon. Each one of these feeds a hybrid that splits the power in 2 and then goes over in 2 waveguides and feeds 2 1-meter sections each. The way this actually gets built in the tunnel is you'd have a separation between 2 sides of the tunnel for shielding. On the right, you have the installed cryomodule over here and space to transport cryomodules as you're building the main LINAC. This is actually the transport to bring the electron beam or the positron beam all the way to the end of the main LINAC. And then on the other side, you have the RF source, the modulator and klystron combined, and an additional one here being transported for installation. Then below the floor, you need a couple of other things. You need high voltage for power distribution, air supply for the workers, and then, of course, drain for groundwater leakage into the tunnel. Taking a little bit of a closer look at the cryomodule itself, you can see that there's these 8-meter-long sections of accelerator, and then shown in this view, they're spaced by these permanent quads, which have been designed to operate at cryogenic temperature. The actual structures and quads themselves are immersed in liquid nitrogen. There's no active pumping of the cryogens in the cryomodules. It's just as the heat is deposited into the liquid nitrogen boils and evaporates, and then it pressurizes the gas above it, and then it returns to the condenser unit. This is the cryomodule that we would use, whether it was for 250 GeV center of mass or even for 2 TeV center of mass or higher. And what's shown here is actually a schematic that would be relevant for the 2 TeV center of mass case. The idea is to put roughly 1 megawatt of cooling located every kilometer or so. So you do reliquefaction every kilometer, the cryogens flow down, and all of the cryo modules are linked with these very wide openings. There's no restriction in the flow for the cryogens. These are just some of the parameters for the operation at 250 GeV center of mass. I think I've talked about most of these, so I'll just highlight that the electrical power for the main LINAC would be around 100 megawatts in this case. Per GeV, this cost comes down as you go higher in energy. It comes down a little bit because you operate with shorter RF pulses. And this would be for 1 × 10⁻34 luminosity at 250 GeV center of mass. So of course, costing studies for linear colliders or for any major facility are of course very, very important because these are expensive machines. We have been working on a cost model for C-cubed, and we continue to try to refine it. We utilize the same format that other linear colliders do, dividing the cost between capital and labor, although mostly our focus so far has been on capital costs because it's difficult to really lay out what the labor would be until you have a plan for commissioning and for building the facility itself. We use inputs either from ClickK or ILC, or at least initially we would use one or the other. And what's interesting is if you compare it for the same case for C-cubed 250, so if you use the inputs from those other collider designs in terms of how much it would cost to, for example, construct the beam delivery system or the sources or the final focus, and then you calculate the total cost for C-cubed 250 using our technology for the main LINAC, you get nearly the same costing between those two sets of inputs within a couple percent. So really, it was quite shocking to me when I saw this, that these two very different designs, but then if you take those as inputs, you can get very close to the total cost for the system. But since then, we've actually switched to using a little bit different of a model. It's a hybrid model. We utilize some things from ILC, some things from ClickK, and some things from our own vendor quotes or estimates or costs that we've incurred in building things. And the reason for that is a lot of the technology is closer to Click, but ILC did a good job in their TDR of itemizing conventional facilities. So for example, it's easier to scale the cost per meter of the main LINAC. So what we see for C-cubed 250 is that roughly 35% of the cost is in the sources. This is the electron and positron sources in the accelerator complex. Another third of it is the main LINAC. 15% is the IP and final focus, beam delivery. And finally, 15% is the supporting infrastructure. I think this is a really critical point. This is a unique position for linear colliders. The cost is not dominated by the main LINAC. And that means that if you make improvements to any of the subsystems, they can now have a significant effect on the overall cost of the accelerator complex. And really, so far, we've just been focusing on the main LINAC, and I think we've made a lot of progress here. But we need to see now what we could do for the electron and positron sources, and to a lesser extent, these other systems as well. So our working estimate for the capital costs for the 250 GeV center of mass case is in the range of $3.5 to $4 billion. This would give you 10% RF margin and 10 GeV energy margin at the nominal gradient. So a little bit of spare capacity built into the system. This, of course, is something we're continuing to work on and hoping to refine as we move forward. Just one comment about labor. Both ClickK and ILC quote a similar cost for labor in terms of FTEs. So roughly between 1.8 and 1.9 FTEs per $1 million of capital cost. But we really need to assess how valid that is for C cubed. It could be different. It just depends on, for example, well, we would hope that our system is a little bit more industrialized, and for example, it'd be easier for a commercial partner to fully integrate the cryo module and possibly even install it. I think we have reached the limit though in terms of cost scaling from ILC and ClickK, and in particular because of what I mentioned before, now that the systems are getting close to equal fractions, we really need to look at this on a specific, basis for each of the subsystems for the accelerator complex. Now, there were a couple questions in the timeline about
Emilio,
why would you want it? Yes.
Before you go to timeline, can you go back
Sure.
to the previous slide? Have you estimated the cost of tunneling, and it's part of your capital cost and distributed among the sources? Or okay. So
Yep.
what is civil construction in terms of total cost?
Okay, so let me break down your question to make sure I get it right.
No,
So we did include tunneling costs. That's in the main LINAC, 35% or so. For that, we utilized the per meter cost of an outfitted tunnel from ILC. And then I think you asked, like, what is the fraction of civil
construction or whatever, conventional constructions? Usually they are kind of separated as kind of total cost of all tunnels and all civil construction, like service buildings and all that stuff. So what it is out of this $4 billion, so what would be the cost of this?
I could tell you with a little asterisk that I'm going off of my memory, but I have those numbers specifically if you're interested, and I'd be happy to share them in detail. But roughly, I think it comes down to about a quarter of the overall system.
Of overall, okay.
Yeah.
And sorry, I probably missed it on one of your previous slides. So the total length of a 250 CO center of mass machine is what?
So the total length of the main LINAC is 4 kilometers. And if you use the ILC design or the CLICK design, it's an additional 4 kilometers. So it's an 8 kilometer machine to get 250 GeV center of mass initially, and then you would upgrade the gradient to get into the 500 range with the same footprint. Now, I'll make a comment about that as well, that if possible, we would want to, of course, make the final focus shorter to get onto a more practical footprint if, for example, this were built at Fermilab. So
we're thinking
from bird's eye view, I think
our maximum is between 7 and 8 kilometers. So
yes,
we can afford.
So well, what it looked like from satellite pictures to me was 7. So that's what I'm going with. But if maybe the fence can be pushed out a little bit and we could get to 8, that would be perfect.
Okay.
So you've jumped ahead to my last slide again. There will be a picture of Fermilab with C cubed on it. So
okay, thank you.
But yeah, the main LINAC is 4 kilometers, and that would get you into this 500 range.
Okay.
Okay, I see we're getting close to 3 p.m. So just a brief comment here. This matches the timeline that we showed earlier, but it's really looking at it from the view of what you would need to do for constructing the main LINAC. And you're talking about producing roughly 200 klystrons per year and 50 cryomodules per year as you're doing the installation. And then during the RF upgrades, so once you're operating at 250, then you bump up the number of klystrons, but you don't need any more cryomodules. And from an equipment perspective, like I said, this is very nice. It's roughly flat funding over the full time, and the production is fairly constant, which I think is great for industry. If you actually check the numbers here, you end up with 10% surplus in terms of klystrons and cryomodules, but you'd either stop building a year early or lower the number a bit, depends on what you'd like, or you have some surplus in stock available in case you need it. So just a brief comment about what comes next in our timeline. One of the key things we need to do is really define what's needed in terms of the demonstration facility And this slide is from the view of what's the minimum requirement that we need. We would need to demonstrate operation of a fully engineered and operational cryomodule, with the possible option to iterate on that. But in terms of putting beam through it, I personally believe we only need one. We would need to, however, demonstrate cryogenic flow that would match what would happen in the main LINAC in order to accurately test the performance under the appropriate conditions from thermal transfer and vibration perspective. We'd want to operate with multi-bunch photoinjectors, so we could do high charge bunches and induce wakes and test the structure that way. And we would want to demonstrate with beam the full operational gradient for the cryomodule. So make 1 GeV in 9 meters. The structure would be identical, the accelerating structure would be identical to what we would use in the 250 GeV center of mass case, fully damped and detuned. And in parallel, we could work with industry to develop the exact C-band source unit that we would install. We don't need this though to wait on the demo facility. For the demo facility, we need 8 C-band klystrons from Toshiba and 8 modulators from Scandinova, and that's it. Roughly, we think this is on the order of $100 million project, 5-year demo facility. It's something that we're hoping to propose through Snowmass MP5. And it's a facility that could continue on with C-cubed relevant R&D, RF sources, pulse compressors, things that would be really important for getting to the multi-TV scale. It could be used by other HEP programs like Gamma Gamma Machine, XCC, or other related fields within DOE, FVL, cryogenic guns, et cetera. And could really, you could also consider doing an energy upgrade, for example, as was mentioned in the case of LCLS. And then as a last slide, sorry, back. So a couple options for realizing something like the demo facility. This is something that could be implemented at SLAC at the End Station B facility. You could consider doing something at the end of LCLS if you wanted to utilize a beam for doing high energy density physics. You could consider installing cryomodules to increase the energy output of LCLS, or for example, replace the injector to do a better job with a high brightness gun or a bunch train. And then I hope somewhat provocatively here we see C-cubed 250 on the Fermilab site. This footprint, at least from my measurement, is roughly 7 kilometers or a little bit over, which is a bit of a problem. The 250 GeV center of mass case is 4 kilometers long for the main LINAC. And if we use existing beam delivery and final focus designs, we need an additional 4 kilometers. If we could squeeze that down to 3, then we could really fit this on the Fermilab site, which I think would be, of course, fantastic for a machine located in the US. But ILC, when it was studied at Fermilab to a much longer length. So certainly we could consider going offsite as well. And that's my last slide. So hopefully this generates a lot of questions and excitement.
Great, thank you, Emilio. That was fantastic. I hope for something fun for everybody to listen to, and it has been. So let's open up for questions. Can you use the raise the hand sign? So, all right, Christoph.
Well, this was the clapping sign.
Ah, it was a clap sign. Okay.
Clapping sign. It was a great talk, really nice.
Yeah. Okay.
I was wondering about this last slide as you just called on me. I think in general, Fermilab is kind of like considered the high energy physics laboratory for the US, while SLAC has at this point veered into a different direction. Does that make any difference here for the considerations?
I think you touched on something that's important, especially for the full operational site. I think having that at Fermilab has some very strong advantages. If we could only realize C cubed by doing the demo facility at Fermilab, that's fine with me. I think, yeah, I want to build a machine or help build a machine that gets to the Higgs. So wherever it can be done. But I think, there's the workforce that's dedicated to this type of research at Fermilab. So it makes a lot of sense.
What is the R&D needed to reduce the length needed for the services? I'm calling them services, but that's also final focus and also the beam delivery initially, right? That part, the bluish part, I guess. What is the R&D needed to reduce that?
So, okay, so the one key question would be defining the exact energy reach that we would want to target. If you could come up with a way to live with only 250 for an initial phase and then modify the final focus for higher energy, I think you could reduce that length, at the outset. But then during the upgrade phase, they're adding in the complexity of redoing the final focus for higher energy. So that seems less than ideal. I think this is, you've touched on something that's a challenge for us to look at over the next couple of months and see if there's any clever ideas that we could implement to try and save a little bit of space. But I don't have any clear.
That's fine. You're not expected to have all the answers today, right?
Yeah. No, it's fair. I don't actually, Vladimir, I don't know if you want to weigh in. If you think would you say there's been any advances in the last, decade or so that could revamp the situation with the beam delivery or final focus?
No, I still have a kind of it's a puzzle for me. I more or less understand that the length of the beam delivery system should grow, but we have slightly different approaches for click and ILC, and I still don't understand the differences. Besides that the energy of click is a little bit higher than ILC, like 380 versus 250. Actually, I have another question to you related to the cost. So you guys kind of put a lot of effort understanding, at least a lot. You made probably more effort than anybody else in understanding the cost of copper-based or RF-based colliders. In your approach, what are the major differences between CCC and click in terms of cost? Where the major cost savings are coming from?
So, okay, so if you compare, so Click did a study in 2019 that looked at what would be required to make a klystron version of their machine.
Right.
It was at 380, so that's one reason why it's a little bit more expensive, of course.
Mm-hmm.
However, if you look at let's say you reduce their design to 250, right, all of the cost savings are in the main LINAC. Yeah. And shorter tunnel as well. Yeah, but it all comes down to the main LINAC at the moment, because we're built off of their cost model, really.
I see. But in your model, main LINAC is not even the major part of the cost, right? It's only 35% of the cost.
That's right. If you look at Click K, the cost is dominated by the main LINAC. If you look at ILC, the cost is dominated by the main LINAC. That's what I think is the huge opportunity here that really just popped out, that for a 250 GeV center of mass, suddenly, if you can save a little bit of money on the damping rings, it has a real effect on the cost of implementing this. So all of a sudden, I think there's other places where we can look now and see if we can make a real difference.
Okay, let me reformulate the question. Cost of main LINAC in your scenario, CCC option, right? So, yep. And cost of main LINAC for click klystron based option, say reduced to 250 GeV. how different they are. I suspect that you're proposing something kind of cheaper, it's more cost effective, but I don't understand what's the scale of the saving.
I'm sorry.
And where does it come from?
So it's a factor of 2, roughly.
Factor of 2.
With their klystron-based option, maybe a little bit more. It's a factor of 3 compared to ILC for the main LINAC. And if you look at where does it come from, and specifically in the case of the klystron version of Click, it's just less RF power.
Because of higher shunt impedance.
Yes, that's right. Yep. Yep.
Sergio?
And the structure is also significantly cheaper, actually. That's another point.
Why so?
So if you look at the Click,
they seem to be bulkier because the frequency is lower, right?
Yeah, great. So that, if I may jump back, the first structure that we built, and it was built by these slabs were fabricated offsite. Everything else was built on site. So this is U.S. lab labor rates was 60 grand finished product, which is extremely cheap.
Yeah.
So it's I have to, well, I think it's a very elegant design. It's 2 copper slabs. A significant cost is actually just in the copper itself. But then the machining is done in a single pass with the one setup in a CNC end mill. And then it's done. So actually getting each of these was only $4,000. First version machined offsite. So it's just a very economical structure to make. If you look at the Click structure, it's a very challenging structure to make because it's these stacked discs, and they have extremely high precision requirements in order to get parallelism between the stacks and to get all of these brazed surfaces to braze together well. Here, for example, we don't even have brazed material in between the RF manifold and the cavities. There's intentionally a gap that's left, and there's only brazed material on the outside. So it is significantly cheaper to make one of these structures than a stacked structure. And then Click, because of its short pulses, has shorter structures. And so they have, I think they have 4 structures per meter, if I'm not mistaken.
Right.
So they have a lot more RF distribute in terms of manifolds and parts, and it adds up. It adds up.
That's why you said the cost of Click main LINAC per, say, GeV is factor of 2 higher than CCC. Then what at least what you kind of estimate for CCC.
Yes,
okay.
That's right.
Sergio.
Yes, thanks. First of all, thanks for extremely nice presentation, for a beautiful last slide. As somebody at Fermilab, that's cute to see. CCC overimposed the Fermilab side. The question I had for you was, I've been looking lately at all the various comparisons of luminosity at different machines, and it's always a difficult task because there are a lot of assumptions about, years of operation and the target luminosity and this and that. I guess the question to you is, and maybe it's easy to, extract it from your slides, but compared to, let's say, ILC luminosity or FCC per IP, or maybe a better comparison would be LEP3. What is the target luminosity per IP per running year, let's say? I think this would be a good number to compare, for example. And my second question was, I think, something along the lines of what Vladimir asked earlier. You show us capital cost of 4 billion. It's very nice. And since you, I think, do I understand that you invested into understanding that the ILC costing model? So would it be fair to say that this number has to be compared to like 7 or 8 billion in the case of the ILC?
So to your first question, the parameters we've picked for 250 GeV center of mass should give 1 × 10⁻34 luminosity, and is shown here on this plot in sort of direct comparison with the original ILC TDR at 250 GeV center of mass.
That's per year. That's per year, essentially, or
Yeah.
that's the total.
This is
Oh,
point
this is
one-
this is
point one inverse Atabarn per year, roughly speaking. Between 0.1 to 0.2, depending on how many days a year you run.
Yes, I think it should be 0.2 because I think after 10 years we get 2. But it's a great question. I have a table I could be happy to share with you.
right, because instantaneous doesn't tell you the whole story, right? It doesn't tell you essentially what's the data taking period you assume.
That's right. So how we calculated the data taking period was utilizing the same off days that were assumed in the CLIC study. And I forget if they match exactly what the ILC study has, but I should double check that. So there is an off period. Basically, you're collecting data only half of the year is what it comes down to. There's like some assumed machine downtime. Then there's some assumed period of off time. Maybe you're collecting data 60% of the year or something like that.
Yeah.
Okay.
And I think more importantly for me on the accelerator side is if you want more luminosity, what you have to do is make the flat top longer, which is something actually that could be done with C-cubed.
That's what you showed earlier, right? Where
yes, that's
right. The test there that we had more than twice the margin from what I saw, and just that maybe I interpreted.
Yeah,
wrong.
we should actually have significant margin. It will, where it will show up as a cost will be in electrical power and in the cryo plants that you need. But it's an interesting study to do as like an alternate option for an upgrade. So you could turn the machine on with some bunch length and then extend the bunch length or the bunch train out to longer bunch train and improve the luminosity just by adding cryo plants. You wouldn't even need to add RF sources in that case because the RF sources that we're talking about can easily operate to 3 microseconds. And in the pulses I showed, they're only utilizing 1.
Mm-hmm.
So it's a fairly conservative starting point, but yeah.
So in the table that you have there, the 75 goes up. That's what you mean, right? But you have more bunches.
So this 75 is for 2 TV center of mass. So the 9 megawatt beam power is for 2 TV center of mass. If you want the numbers for where did I put them?
It's all right.
Oh, here, I'm sorry. 133 1 nanocoulomb bunches over 700 nanoseconds for 2 megawatts of single beam power. Oh, I'm sorry, I have a typo here. I'll change this in the slides before I send them out. That's for 125 GeV.
Yeah, no, I can understand. You did it in such a quick period of time, then from a TV to 250 GeV center of mass. So there's some things there. By the way, I think we should be careful about this dollars numbers that were presented in this talk, and they're not necessarily all set in any particular way. So we should probably not advertise it too much.
Yeah, you can ignore my second question if you want, for the purpose of not recording it.
Oh, that's okay. So the caveats, and I apologize, I sort of forget the question that you asked, but let me be very clear about the costing numbers. We derive everything from ILC and CLIC-K inputs, plus numbers that we can back up with from the for example, the structure cost, we actually built one and we know how much it costs us in lab dollars. So, but, we do utilize ILC and CLIC-K very heavily in terms of getting the overall cost. And could you remind me what your question was about?
Yeah, the actual question was, is it correct to say that the capital cost is essentially roughly 1/2 of what's the expected cost of the ILC at 250 GeV? I don't want to put you in an uncomfortable spot, so if it's fine if you don't want to answer this. I was just I was just asking to see how much gain is there, but I understand it's a sensitive topic and it's hard to make those comparisons side by side.
It is hard to make those comparisons. This is I'll just say this is what we calculate for our capital cost, and we're gonna try to make it lower over the next year by doing a better job with the design.
I think for the ILC, the number is close to 5 billion in these units. So it's a 20% savings. But if you consider that it's all coming in the main LINAC, it's much more significant there.
Okay, thank you.
Yeah, I think that's for 250, right?
250.
Yeah, I think the
And
7
this
is
machine, I guess, is, well, we don't know about the upgrade from 250 to 500, but the strategy for getting from 250 to 500 doesn't involve any additional tunneling.
That's right.
So that potentially could be much cheaper.
Yeah. It's 1.5 billion if you just upgrade the RF with catalog items today.
We have kept you for 20 minutes extra already. So if people want to leave, that's fine. I don't know how much longer Emilio wants to answer questions, but yeah.
I'm happy to stay. I can stay an extra 10 minutes, but then I also have to run.
If there is anybody who wants to ask a question right now, that would be good. Otherwise,
Last quick one, Emilio, on your last slide, when you show map of Fermilab with this perspective collider, I see CCC 250/500. What does it mean?
Oh, this would just be the same footprint for whether you'd start at 250, but you'd also operate at 500 here. You wouldn't add main LINAC.
But here, as far as I see, 7 kilometers is good only for 250 GV machine.
Well, we would do an RF upgrade and we would increase the gradient.
From 120 to 240 or what?
No. From 70 to 120. And then there's some margin in the length of the LINAC and there's some margin in the RF power.
Oh, you're saying that even 500 GV machine fits this 7 kilometers. I see.
It doesn't fit 7, so that's the not quite.
Not quite, okay.
So you need a little bit more.
Well, this is the question of how long the BDS has to be.
Yes, exactly.
Right.
Yeah, that's the question that I was asking.
The idea is that it would be the same footprint for 250 and 500.
Right.
But the BDS, we have to understand whether that's enough.
Right.
The ILC BDS is designed for a TEV.
Mm-hmm.
So it's possible you could scale that back, and it just has to be studied.
Right. Yeah. So there is good chance that for 250 GV machine, BDS can be squeezed to like 3 kilometers.
Maybe.
Right.
But let me ask you the opposite question. Is it really important that this machine fit on the Fermilab site? In the ILC TDR, it runs north-south a much longer distance. Is that feasible, or it's considered not to be feasible at Fermilab?
I think that's for you, Vladimir.
Vladimir can represent Fermilab.
I have
or any Fermilab.
I have only one data point to form any judgment on. And that is that the last time when we showed these 30 kilometers lines, which are crossing Fermilab and going north-south, our effort ended in negative result. So I think we can continue considering bigger machines. It's not a problem in principle, but having options considered which fit Fermilab site, I think it's quite important for general information. I believe Pushpa is our leader of Fermilab Collider group. So I believe one of your efforts is to figure out what kind of colliders or future machines can potentially fit Fermilab site and see whether there is a physics what is the physics which can be done with them. Is it correct, Pushpa?
Yeah, I mean, I was actually very happy. Thank you very much, Emilio, for this talk. I was very happy that we could add this one to the list of our site fillers, Fermilab site fillers. Because, I mean, I think it's our easiest option, right? If a machine can fit on Fermilab site, it kind of immediately reduces a lot of other complex issues that otherwise we'll have to address. So,
But-
so
But on
this,
the other hand, there for the C-cube machine, there is a vision of going to 2 or 3 TeV and maybe further. And
yeah,
that definitely will not fit on the Fermilab site.
that's what I was, I was going to raise. I mean, what is the ultimate energy that we would actually like to achieve? But again, that's all going to depend on the cost, right? I mean, if it's extremely expensive, we probably able to go to the TV. So let's take whatever we can. So-
Okay.
I was going to bring up another possibility. The Fermilab has another site. It's called South Dakota.
South Dakota site, yeah.
Yeah,
Well, I mean,
so maybe land is not an
Yeah.
issue there.
I don't know how much land we have. Vladimir, do you know? Is there land?
Oh yeah,
that
I think we
under-
have a spot of land, but vertically you can go down to
Yeah,
the center of
that's right.
Earth.
Maybe along the shaft.
6,400 kilometers, all yours.
No, but there's plenty of land in South Dakota. I think where buffaloes roam, you can do a lot more. Real buffalo.
We can certainly consider, sites outside Fermilab for multi-TV machines, but I think it's very nice that this machine up to half a TV, which was the original ILC, interest, it fits on Fermilab side. That's really a great selling point.
Mhm. Yeah, we're going to try to really nail that down for with this question about the beam delivery, because I think for getting something off the ground, we want to stay within defined boundaries so that you don't get into some legal. I mean, could you imagine if like the project is approved and then you get stuck in some legal fight? That's what takes it out. Oh man.
Considering the kind of things that we got into for even using neutrinos coming out of reactors in the past, it's not really a great idea to go for this type of difficult negotiations with neighbors of Fermilab. I think that we had trouble even with access to the lab roads, right? It's just not.
But I do think it would make a lot of sense though to position it. The problem with the 7-kilometer version here is that it only fits in really in one sort of one orientation and maybe not one that makes sense for multi-TV. But
I mean, certainly we should consider off-site locations and longer machines, but yeah.
Is this, does the Fermilab crowd know if these are really the boundaries of the site or only the like fenced in boundaries? Does the property extend any further?
I mean, I think we have to investigate that and get back to you on that.
Okay. Yeah, it might be interesting to know sort of what the preferred orientation would be as a constraint.
Yeah, in fact, I have tried to draw all sorts of things for to see if an ILC 250 GV can be somehow fit by having some lower energy options, elsewhere, and then have a diagonal linear part. But they are on my board trying various scenarios. So it's nice to see that you can have the whole thing in one straight line.
Okay, I think that we should probably stop now and thank Emilio. I do have one question though. Many of us can be cheerleaders as particle physicists. In which way can we help to advance something like that besides cheerleading?
We've reached the stage now where we need to start growing the C-cubed collaboration beyond. I mean, we already have some partners, of course, beyond SLAC, but I think we really need experts in all capacities: the sources, cryogenics, the beam delivery system. So getting people on board who would be interested in that would be fantastic. And that's going to be one of our goals going forward.
So thank you, Emilio. So thank you very much for short notice and giving us a wonderful talk. I think this prepares you for lots of talks in future.
Yes, that was good. I will send a PDF of these slides if you're interested in sharing them, and make sure that all the figures show up. I have no idea what happened. It was an interesting glitch. I'd just gone through them like 10 minutes ago. So or
All
10
right.
minutes before the talk.
All right.
Okay. Thank you, everyone.
Thank you.
Thank you.
Thank you for joining.
Thank you.
Bye.
Great talk. Thank you, Emilio.
Thank you.